Hello and welcome back to the A4Q Global Testing Summit. I am now delighted to welcome Jean-Baptiste Crouigneau. He is a consultant in software testing and quality. He's also the founder of the Progideo Consulting Office, and he's also working as an ISTQB and IREP trainer, and also the founding member of the CMTL, the Moroccan Software Testing Committee. In his presentation, he gives us an introduction to quantum computing and introduces us to the highlights on what software testing could mean for such computers. We are really looking forward to your presentation, and for the audience, feel free to ask questions. We are happy to answer them.
Thank you. Thank you. Hello, everybody. I'm very pleased to be with you for this new A4Q Congress. So today I will talk about quantum testing. In fact, we will see a little bit of quantum physics and quantum computing because it's a requirement before to talk about software testing in the quantum computing environment. So that's why I titled my presentation Quantum Testing Part 1, because maybe if someone asks me to, I will do a Part 2. So we will mainly speak about, but just, of course, some very highlights on quantum physics, quantum computing, and just a few leads at the end about software testing on quantum computers. So first, a few words about quantum physics. I'm not at all an expert of quantum physics nor on quantum computing, but anyway, there is very few experts in the world. So just I'm curious, so I will try to share this curiosity with you. And we will see just a few effects linked to quantum physics. Maybe you learn a little bit at school some quantum physics. It's not very easy. It's sometimes difficult to imagine or to make it concrete. So I try to make it very simple. But we, in quantum computing, we use some specific quantum effects. And the first one is called quantization. Quantization is just means that for quantum particles, the characteristics like energy, like speed, like size, or something else, very often are not continuous measures, but instead discrete values. For instance, an electron has a charge, and it can be 1, it can be 2, it can be more, but nothing between 1 and 2. So when it changes the level of charge, it goes directly from 1 to 2. That's a little bit strange, but that's the way it works as far as we know for now. So that's the first phenomenon or aspect, quantization. Quantum particles have some discrete values when you try to measure something on it. Second phenomenon called wave-particle duality. It's a little bit known maybe, but still it's one of the strange effects in quantum physics. To explain that, there is an experiment. So this is a modern version of this experiment, but you can emit some photon, so one by one, for instance, in the direction of 2 slots. So it's why it's called the double slot experiment. And then what we can see on the screen that is behind is not one or two ray of lights, but instead a pattern like interference of light. So you have some line of lights. And the only explanation for that is that the photon behaves exactly like a wave, meaning you have a wave, and when it reaches the two slots, it's split in two waves with interference, and you can see it on the screen. So that's okay, that's an experiment, and that's how it works. Now, let's try to add some detectors just on the slots. We do not interact with the photon, just we want to detect if maybe it goes through the right slot or the left slot. If you do that, then suddenly the pattern change. You have no more interference, but you have just two point of light here. And now each photon goes through or the right slot or the left slot, because the detectors help to know that. So suddenly the particles behave exactly like particles, not waves. So it's the same photon, but it behaves completely differently. Just because we try to detect where it goes through. And even maybe stranger, there is another experiment, but I will do an analogy here. If you try to detect the photon farther, just before the screen, then you have exactly the same behavior, meaning behave like a particle. And it's very strange because it's like the photon choose to act like a particle even before to be detected. So it was like he anticipated that there will be a detector, so now I'm a particle, I'm no more a wave. We can't really know why for now. So it's called the wave-particle duality. Quantum physics is very interesting because it's very strange. So two more important phenomena. First one, superposition. Superposition, means that particles have several values at the same time. Let's try an example, for instance, a photon. There is a polarization that can be or vertical or horizontal. In fact, it's not vertical or horizontal. Before you measure it, yes, when you measure it, you will find that it's or horizontal or vertical. But before that, it's a little bit the two at the same time. In fact, there is some probabilities that it's both vertical and horizontal. To explain this phenomenon, also a quite famous, it's not a real experiment, it's a fictive experiment, but it's called the Schrödinger's cat. And the Schrödinger's cat, imagine that you put a cat in a box. You trap a cat in a box with a bottle of poison, closed, of course. You have also a hammer on the top of the bottle and a trigger, a switch to maintain the hammer. That is triggered by, well, the detection of the disintegration of radioactive atom. Okay. So atom will disintegrate after a certain time. So you have let's say 10 minutes, and after 10 minutes, you have about 50% chance that it will disintegrate. But it's not 100% chance. So at that time, we can say that this atom is both intact and disintegrated, both at the same time. That's what quantum physics told us. So we could say that the cat is both dead and alive at the same time. Once again, a little bit strange, and in fact, nowadays it's a little bit disputed, like explanation, but it makes things a little bit concrete, so it's useful to explain superposition. And it's very important for quantum computing, like we will see later. The last very important effect is entanglement. Not easy to say for me, but entanglement is what? Let's consider some photon. Photon can be generated by some atoms like cesium, anyway. So they both came up from an atom of cesium, and they are entangled because they come from the same source. We just saw that due to superposition, until we measure the polarization, for instance, of this photon, they have the both value, vertical and horizontal. We can't know. They have 50%, let's say, of chance to be or horizontal or vertical. And in fact, they have the both value at the same time. Then, later, we can measure the polarization of the first photon. Let's say it's vertical, okay. What is very strange at that time, that is at exactly the same time, the other photon choose exactly or the same or the opposite value with no time. That means that they can be at light years away, very far away, because they go to the speed of light, of course. But it's like they exchange some information. The first photon tell the other one that, okay, I choose vertical polarization, so you have to do the same, or the opposite, it depends on the characteristics. But so it's like they exchange information faster than the speed of light. Very strange also. Unfortunately, we can't transfer information faster than the speed of light, just because the issue, we can't know the value, in fact. So we can't choose a value by ourselves to transmit a value to the other photon. So it's not useful for that, but it's very useful for other effects, like we will see. Okay, I won't do too much more on quantum physics. Just indetermination. Indetermination means what would you like to say? Yes. Let's start for non-cloning. Non-cloning is simple. It just means that you can't copy a characteristic of one quantum particles to another quantum particles. In fact, just because of superposition and other effects. So it's very important because, in fact, when we use some classical computers, very often we copy some data. Here, we can't copy quantum particles. That's maybe an issue. Yes, and indetermination means that when you measure one characteristic of, let's say, a photon, you can't know exactly the other characteristic. So you can't know both two characteristics at the same time. So you can only measure one characteristic. The other one will be then undefined. Okay, so a lot of strange things in quantum physics, and all these effects can be used to create, to make some quantum computers that already exists. I don't know if everybody knows that, but you already have some quantum computers, but as we will see, they still have a lot of issues with these computers. That is why it's not used everywhere. So let's see a few differences between traditional computers and quantum computers. In a traditional computers, you have bits, so value 0 or 1, one or the other. And it's exclusive. It can be something in between or a mix of this. It's or 0 or 1. For quantum computers, we will have qubits. Qubits, so still we can use some binary characteristics like photon polarization and associate it to or 0 or a 1, but a qubit can also have a probability to be something between 0 and 1, meaning he didn't choose really if it's a 0 or a 1. And we will use this because it means, in fact, that during the calculation, it may take a lot of values, not only 0 and 1. But at the end, it will be or a 0 or a 1. Another point is registers. So like for traditional computers, we will have registers, but not registers of bits, but registers of qubits, of course. It's more or less the same. We will see how it works exactly. But to transform the values, we will use not logical gates like in traditional computers, but quantum gates, very special gates. There is a lot of different gates that will transform the state of our quantum particles to make some very complex calculation in a very short time. Then the last very important point is measurement, because of course we do not measure just some electricity effect, but some more complex characteristics. And measurement is one of the issues because it's not very reliable. So sometimes you may have errors during the measurement. And we will talk a little bit about quantum coprocessor. So first, just qubits. Well, you can forget all the equations. We just have a look at this sphere. So we call it the Bloch sphere. I pronounce it like this. It's easier for me, but anyway, it's just a representation. It's not the reality, but it's very useful because on this sphere you can see at the top it's 0. At the very bottom, it's 1. But all the rest of the sphere is possible state of the quantum particles. And we can represent the actual state by a vector, a psi vector is here. That means that if the vector is in this position, you have a certain amount of probability that the value is a 0, but not 100% probability. And also, of course, a certain amount of probability that it is a 1. And these vectors will change during quantum calculations. It's just at the end, we will make a measurement, and then at the end, the qubit will have or exactly the 0 values or the 1 values. But it's only at the end. We can see it on this slide on qubit registers. So registers here are like traditional registers. So it's several bits. Here you have only 4 qubits, so not 4 bits, but 4 qubits. And 4 qubits can have, in fact, 16 different values for the register, from 0000 to 1111. Then we will apply some gates, what we call quantum gates. For instance, just a gate only on the first qubit. These gates, we don't have to detail how it works, but will transform this gate in the opposite value. So it is at the beginning a perfect 0, then it becomes a perfect 1 with 100% probability. Until now, it's quite like a traditional computer. Then we use another quantum gates, this time on each qubit, and this time it will change the probability to an equal probability to have a 0 or a 1 on each qubit. So the probability is the same for every value of my register. The registers can have any of the 16 values with an equal probability. And then a last quantum gate. This one is different because it uses the 4 qubits at the same time in the same gate. And this one, once again, we can't enter in all the details, but we'll transform this in a perfect, a 100% chance to have 1, 0, 0, 1. That's how works quantum computers. It works like that in an ideal world. So in reality, it's not exactly this because you may have some errors on each gate and on the measurement. But the goal is that it should work like that. Here, a little comparison between the classical logic gates that we use in our computers. So with some truth table between inputs and outputs. So you have some inputs and you always know exactly what will be the output. For quantum gates, it's a little bit more complicated and even much more complicated in some gates. So you can see here some matrix. In fact, we won't transform a 0 into another 0 or a 1. We will work on the vector in the Bloch sphere that we just saw before. So that's why we use matrix, and the vectors will change his position inside the sphere. So we have some very simple gates and some much more complicated gates. There is a lot of gates, and some new gates can be created not every day, but depends of scientific and mathematical researches. That's it. So traditional computers, it transforms some logic between input, output. Quantum computers or gates, it's a little bit different. Most of the time, we start with a register full of 0 because that's something that the quantum computers can do. Then we will put some gates. So that is the quantum algorithms. We can say that is the software for us. It will transform this through several gates, and at the end we will measure the value, and we will measure a specific value. The problem is, like as already said, we will have some errors in each gate and at the end when we will measure the value. That means that if you make twice exactly the same calculation, you may have a different result. That's a big issue for quantum computers. That is why, for now, when you want to use a quantum computer, you have, in fact, to do a lot of calculation. I mean, several times the same calculation, and at the end, try to make an average of all the results to get the most probabilistic result. So you make an average, and it should be now deterministic, meaning that you will have a good result. But for this, very often you have to do a lot of cycles or a lot of times the same calculation. As you can see, for nowadays quantum computers, you can do up to 8,000 times the same calculation to have a good or fairly reliable result. Okay, I advance because time advance. So just a short view of quantum computers. So quantum computers, in fact, it's not really a pure quantum computers, because if you use only a quantum processor, you can do very complex calculation. Oh yes, very important things. Huh? It means that, for instance, in theory, some calculations that may take billion years for a supercomputer nowadays may be done in a few minutes by a quantum computer. So when it will work perfectly, of course, it will change a lot what we can do. But in fact, our quantum processor is more a co-processor. It means it will be used only for very large calculation, but all the rest, the graphical interface, the storage of the data, because we can't store qubits, like I said, the daily calculation will still be made by a traditional computer. So we will still have a traditional computer, some electronics, of course, to control the quantum coprocessor that have to work at a very, very low temperature, very even next to the absolute zero. So it's a big installation with a lot of energy. And you see here an example of quantum coprocessor, quite original. I don't know if it's beautiful, but yes, a little bit. So that's how is designed nowadays a quantum computer. So quite big, of course, very expensive, but you can buy a quantum computer. You have some companies like D-Wave company in Canadian company that makes and sell some quantum computers. So, to finish my presentation, or just a few minutes, a little word about software testing, because It's, of course, our subject in this Congress. Of course, there is a lot of tests to do when we want to use a quantum computer. You have first the quantum computer itself, meaning you have to test the hardware, the gates, the measurement devices, everything where we know that there is a lot of errors. So you have also some error corrections devices. All this have to be tested, but it's more hardware testing than software testing, to be honest. Then you have also the coprocessor controller. Here it's a mix between hardware and software. You have software to control the coprocessor, to control how we will initialize the qubits, which gates we will use, and how many times we will do the calculations, all this. So here you already have some, of course, software testing to do. Not to do every day because it's part of the computer. So it will not change every day, but still it has to be tested. Then you have the quantum, let's say, software itself. So you can test it on quantum computers, but also on quantum emulators. People who work on that use a lot of emulators because it costs, of course, less than the quantum computers, and it works perfectly compared to a quantum computer. It makes no error. The issue, of course, is that it's very slow compared to a quantum computer. So you won't have all the advantage of a quantum computer, but you can design and test your software on an emulator. So you have to test the software, but also the emulator itself, because it's still experimental. We don't know exactly if it behaves exactly like the real computer. You have to test the gates. If you create a new gates, it's very complicated. It's for very high-level experts. But of course, you have to test also the gates in theory and then in the quantum computer itself. So a lot of tests to do, but I can't develop much this part because I have no time. But as you can see, we will be able, maybe in another presentation, to speak about verification, validation, black box testing, white box testing. So there is a lot of parallel between classical software testing and what we could call maybe quantum software testing. So that's totally new. I think I don't know if there is someone who is really working on software testing on quantum computers, but just I was curious, and that's why I work on this subject, to know what it could be or what it will be in the future. Future that maybe in a few years or maybe later, because there is a lot of specialists that think that it's still far away to have some good quantum computers. But let's hope maybe in a few years we could use this kind of computers. A last slide to quote a very important book by Olivier Ezrati. It's a free book, more than 800 pages on quantum computing. So you will learn about all what we know actually on quantum computers. It is updated each year, and it's really these books that make me think about this presentation. It talks about physics, about computers, but also about social effects of computers, quantum computers, when it will be effective. So just a word on that. Just think about, for instance, cryptography. That's a very important problem in our world. And cryptography works because often to break the encryption or to decrypt the message without the encryption key, you need sometimes 100,000 million years of calculation for a very, very big computer. So nobody can do it. But with a good quantum computer, you can do the same in a few minutes. Then all the encryption algorithms that we use nowadays will be obsolete. It will change a lot of things. Of course, probably we can find some new way to protect our data, but that's, for instance, one of the social effects that it could be have. And finally, also, you already have, like you can see in all the big IT companies, some solutions to develop some quantum software or algorithms, more precisely, using some tools to make some code. You can test it on emulators and even on real quantum computers. So sometimes it's you have to pay for that, but you have also some free solutions, so you can very easily find some tutorials and try in a few minutes. It's very easy to make your first quantum software and try it and see what is the result. Okay, that's it. I hope that I'm on time. Of course, if you have questions, you can give me later or whenever you want. And I hope that it's interest some of you, and maybe I could make a new presentation to go more in details in the testing aspects. Thanks a lot, and see you later.